So that was one of the obvious things we could solve for, but there's something else we could solve for. We know that the two blocks are going to be accelerating at the same rate. M1 and M2 are both going to have the same acceleration, 1.66 meters per second squared to the right. But there's one piece of information that's missing. We're not sure what's happening inside this rope here. We don't know what the tension is in that rope. So let's go back and solve for the tension in the rope now. And I'm just going to use equation 1 to do that. That's the tension equals M1A. And I get my tension is 6.77 newtons. Alright, so make sure your answers have correct units, and make sure if they are vector quantities that you have a direction associated with them. For the tension in the string, I'm just going to leave that tension. I've shown my directions here. Acting on M1, it goes to the right. Acting on M2, it goes to the left. And the magnitude, I guess just to be sure you understand, this is just a magnitude here. I could indicate that. The magnitude of the tension is 6.77 newtons, and it acts in opposite direction on the two masses. So let's do a quick system approach to this problem. It won't take us too long. And what we're going to do, I'll just redraw it here real quickly. You've got M1, you've got M2, you've got a force over here, and a tension over there. And what we're going to do is treat this whole thing as a system. And we're going to ignore the internal forces, because the tension, it's pulling on M1 from M2 and M2 from M1, and it's not helping this system move any faster. It's not helping it accelerate or hurting it accelerate. It's sort of like sitting in your car and pushing on the dashboard. Your car's not going to go any faster, right? It's the internal forces cancel out, and all we care about is what's reaching into this system and causing the whole system to move. So this is nice because it gives us, what we end up with is one equation and one unknown for our acceleration. All the internal forces cancel out. So we say sum of the forces on the system is equal to M system A system. And what we can do to find the sum of the forces on the system is actually just look at the free body diagrams and add them all up. And so what we care about right now is the direction of motion. Let me just sort of draw a yellow line through my direction of motion is here. And so the first thing I see is a positive T, a tension in my positive direction. I'm going to be jumping back and forth here a lot, sorry about that. The next thing I see is a negative T, a tension in the negative direction. And then I see a positive F, and those are the three forces I see. Let me go back up and show you that. First thing I saw was this tension in the positive direction, then a tension in the negative direction, and then a force in the positive direction. So those are the three. I just added up all my forces in the direction of motion, and what happens to my internal forces? They cancel out, and then I'm left with the mass of my system, which is M1 plus M2, and the acceleration of the system we're just calling A. Another way maybe to look at it is to look at this dashed box right here, and the only thing that reaches into that dashed box is F. So we have F is equal to M1 plus M2 times A, and that's exactly what we got earlier. So we end up with A is 1.66 meters per second squared to the right, and that's a little simpler, right? We don't have to solve simultaneous equations. And you might be thinking to yourself, well, two equations, two unknowns, that was pretty quick and easy. Why bother with this other approach? Well, because sometimes we have more than two masses. Sometimes we have three masses, and then you have three equations and three unknowns. Sometimes we have four masses, and then you have four equations and four unknowns. But this system approach, all those internal forces cancel out, and you can solve for the acceleration right away. Now, if you were asked for the tension, or you wanted to solve for the tension, you would have to go back to one of your individual equations, like equation 1 or equation 2 here, and plug in your acceleration that you got using the system approach and find the tension. So that it is a two-step problem there, but it makes it quick and easy to find the acceleration using this system approach.